of information that will be made available to the battlefield. Isn't there a danger of too much information?
Maybe a better way of saying it, there's a great deal of data available, and when you digest it, it becomes information. What we're trying to do is to put a lot of processes close to the sensor so that you don't have to transmit a lot of raw data, but you do some interpretation, as it were, at the sensor, and then transmit the digested information, of which there is less than the raw data. There indeed is a tremendous amount of information. It's a problem.
Any other questions? Okay, thank you very much, Leo. I'll run your view dress for you. Our next speaker is Dr. Angel G. Jordan, who is Provost of Carnegie-Mellon University. Prior to becoming Provost, he was Dean of Carnegie Institute of Technology and Professor of Electrical Engineering. Dr. Jordan is a native of Spain and earned his doctor's degree from Carnegie Institute of Technology. He is a fellow of the IEEE. Under Dr. Jordan's direction, Carnegie-Mellon in 1960 established one of the first training centers for integrated circuits engineers in the United States. And from these centers, there were about 3 of them at the time, a whole generation of device physicists emerged. I'm pleased to introduce Provost Angel Jordan, who will discuss the changing relationships with defense in the engineering schools and in computer science at universities. Provost Jordan.
Thank you very much, Harvey. I am representing a university. I am an electrical engineer. And in universities, we have very good relationships with the Department of Defense, but people are our most important product. Somebody said that before, but it was progress, right? In fact, one of the products is Harvey Nathanson. He's my first PhD student. This is why he's so kind to me. My role is to talk about the universities, with defense, with industry, and the new relationships, which are not so new. They are old. But I think we have rediscovered the industrial connection. Give me the first transparency, Harvey. I think you will know that the Department of Defense, and I am amplifying some of the statements which Leo Young was making before, has a tradition. It doesn't go for a long time, but in the last 25 years, the Department of Defense, DoD, as we call it, has funded research in universities in a number of areas. In engineering schools, in computer science, and I'll elaborate about that later. It's a branch of electrical engineering, but it's also a branch of mathematics. In material science, and this is key, because materials are used prominently, and they are well funded by the Department of Defense and later by the National Science Foundation for making the devices out of which you make the circuits and out of which you make the systems. Electrical engineering and computer science have been key beneficiaries of the funding coming from the Department of Defense for good reasons. As Leo Young mentioned before, the bulk of the electronics is basically electrical engineering, although it relates to physics, chemistry, and computer science. The research which we conduct in universities with funding from the Department of Defense and funding particularly from the National Science Foundation is by definition fundamental. But applied research is conducted without apologies in universities, particularly in electrical engineering departments. The line between fundamental and applied is extremely fuzzy. Very often, applied research, which is quasi-science, but is engineering, is extremely fundamental. And very fundamental research, particularly in computer science and in software, is extremely applied. So let's not make a very abrupt distinction between the two. I cannot read from here. Yeah. Can you focus that a little better, Harvey? Because if I cannot read from here, probably... Mission-oriented research. Yeah. Mission-oriented research. Universities conduct mission-oriented research without apologies. It's traditional for university administrators and sometimes professors to argue that mission-oriented doesn't belong in universities. My philosophy and the philosophy of many professors in universities is that there is nothing wrong with conducting mission-oriented research. We don't do development in universities, but research, fundamental or applied, particularly in electrical engineering, in electronics and in computer science, has to have a target. And often, in the process of conducting that type of research, we find that new fundamental science is created. Give me the next one. However, in universities, we shy away from classified research. And this was the bullet I had in the previous slide, in the previous transparency. Universities, by tradition and by mandate, shy away from classified research. But we do defense research, which is non-classified, and often leads to further research, which is classified but not conducted by universities. Although it has been mentioned by Leo Young before and by the president of the IEEE, let me just give you the names of the agencies in the Department of Defense which have been funding research in universities. The Office of Naval Research was the first agency. It's the scientific branch of the Navy. We call it ONR. Everybody knows what ONR is. It's the Office of Naval Research. It preceded the National Science Foundation. The Office of Naval Research was the first government agency to cater to universities. That was not the only mandate of the Office of Naval Research, but indeed a good chunk of the funding from the Office of Naval Research went directly to universities. And in fact, even before computer science was a field or a discipline, it of course went to electrical engineering, it went to mathematics, to physics, to material science, and to chemistry. The scientific, the counterpart of the Navy, of the Office of Naval Research, is the Air Force Office of Scientific Research, AFOSR, which is at the Bolin Air Base here in the Office of Naval Research, operates from Arlington on Wilson Boulevard, and is well known to many of the professors of electrical engineering, many college presidents, and many provosts who pay periodic visits to the Office of Naval Research for good reasons. The Air Force Office of Scientific Research, AFOSR, is the counterpart. It caters to universities pretty much in the same way as the Office of Naval Research caters to universities, but the money comes from the Air Force from the Air Force. There is, of course, a counterpart. Harvey Nathanson was talking about the jealousies or the rivalries of the different agencies or the different parts of the Department of Defense. The Army Office of Research is in North Carolina. It's not in Washington. That makes the trips from universities a little more expensive, but we go there often. Interestingly enough, the three agencies, ONR, AFOSR, and the Army Research Office, have different ways of funding the universities, although they are similar in many ways. For instance, the Office of Naval Research, when it funds or entertains proposals from universities for research for the Department of Defense, often it reviews the proposals internally, although occasionally they go to external reviewers. They have, however, extremely competent staff because they are scientists or engineers, particularly electrical engineers, and they have in-house research programs which are complementary to the research programs conducted in universities. The Air Force Office of Scientific Research reviews the programs or the proposals from universities, sometimes connected with industry, in a similar way. They have internal reviewers, but they go outside for external reviewers. The Army Research Office, which incidentally has the smallest funding of the three, because they have more developmental research R&D laboratories in-house, does the review for university proposals with the National Research Council. They go to external reviewers. In a way, the proposals from university are peer review, pretty much the same as they do in the National Science Foundation. Leo Young mentioned the Joint Services Program, the JSEP program. This is a very interesting concept which has been extremely good to universities, not because of the money, because of the impact which this program has had in the training and education of students and professors. The concept of the Joint Services Program is that the three, Army, the Navy, and the Air Force, pull together resources and they block fund universities. In fact, that was the beginning of the well-known electronic laboratories, and there are a number of universities in this country, the prestigious university, which have blocked funding from the joint services. Next transparency. What I am telling you is that the Department of Defense, through the three agencies, plus ARPA, plus the joint services, together with the National Science Foundation, have actually funded the lion's share of the fundamental, applied, more fundamental than applied research in universities, particularly in electrical, electronic engineering departments and computer science. Well, what have we done with this funding? Before World War II, there was no provision for funding of fundamental research in universities. The researchers were doing research, often without any funding. And there was industrial funding, but it was for purely developmental projects complementary to the fundamental research done in universities. What has happened after the Second World War, which is the Office of Naval Research, the National Science Foundation, later the Army Research Office, the Joint Services, etc., although the Joint Services preceded the Office of Naval Research. I have just to give you a few names of areas which have spearheaded the new electronic industrial revolution. Information theory came from universities. Coding theory and practice came from universities. Now, packet switching, which is the way of transmitting information through computers in a special way. The significant developments came from universities, in concert with industry, but funded by the Department of Defense. Estimation theory, which is the precursor of adaptive control and communications, and plays a role in both. Computer graphics, where you have seen significant developments in industry, the beginnings of computer graphics emerged from universities. Robotics, we have not invented robotics in universities, but many of the fundamental ideas in adaptive control are now finding their way in robotics. Image processing, in which industries have made tremendous contributions. The beginnings of image processing was in universities. Pattern recognition has many applications in signal processing, in radar, in sonar, now in computer graphics and in robotics, in medical electronics. That emerged from universities with funding from the Department of Defense and the National Science Foundation. Biomedical technology started in universities. You all know about the Silicon Valley, Route 128, why those developments were spearheaded in companies but near universities. However, there is another valley which has not been publicized as much as the Silicon Valley near Stanford and Berkeley, or Route 128 near MIT and Harvard, the Bionic Valley, which is at near the University of Utah, well known for tremendous contributions in biomedical engineering. I think since I am talking about the mechanisms and vehicles for the Department of Defense to funnel funding to the universities, it might be a good idea as a complement to some of the presentations made by Leo Young, that I'll tell you how the breakdown roughly of the funding comes from. This is a typical university, happens to be my university, but it's not the breakdown in funding, and I'm not giving you the total amounts, I'm giving you just the breakdown is roughly as stated on that particular transparency. The Department of Defense at this particular university, which happens to be mine, and it's not very different from other universities, well, number one, 2/3 of the funding for research in electrical engineering, in computer science, in material science, in physics, the basic areas which produce electronic and microelectronics, 2/3 comes from federal funding. And of that, the Department of Defense contributes roughly 32%. The National Science Foundation, close to 20%. The Department of Energy, which is not represented at this conference, contributes an amount much smaller than the Department of Defense. Health and Human Services, which includes the National Institute of Health, contributes an amount much less than the Department of Defense. Now, when I say that this is a typical university, you have to understand that this particular university doesn't have a hospitals, and doesn't have a medical school. In institutions where you have a medical school, the National Institutes of Health contribute more funding. Stay there for a moment. Where does the rest of the funding come from? Well, the so-called industrial connection. Now almost 16%, in some other institutions is almost 20% of the funding for research, both fundamental and applied, comes from industry. When the Information Technology Center is something which is indigenous to my institution, is roughly 5% and is basically industrial funding. When I say other non-federal, we are talking here about state funding mainly. As you can see from this transparency, the lion's share of the funding for both fundamental and applied research in universities, particularly electrical engineering and computer science, is the Department of Defense. Okay, let me talk a little bit about the new modes of operation for industry. As I said before, at the beginning of my presentation, universities have rediscovered the industrial connection. There are many industries now coming to institutions, to academic institutions, to do research. And there are many modes of operation. Very often, these industries do enter into an agreement with an institution to do research in which the industry benefits directly. Another way of doing research in universities with industry now is to have consortia of companies funding generic research in particular areas. Areas which are of interest now for industry, and of course the original funding came from the Department of Defense, our VLSI, and you know the very large scale integration, CID, which is computer-aided design, which is extremely popular now, and much of the fundamental research in computer-aided design is done in the universities. Computer-aided manufacturing, CAM, or the combination of both, CAD, CAM. As you know, these are the ingredients for automation, particularly flexible automation. Areas in universities, particularly in electronic engineering and computer science, which are popular and are funded by industry, is optical data processing. In my institution is funded by Westinghouse, not through the auspices of Harvey Nathanson, but his boss. Magnetics technology is an area which is not well publicized, and probably you members of the press are not as familiar as you are with conventional electronics. I am here referring to magnetic recording. It's well known that the silicon chips, the microelectronics, the VLSI is extremely hot and very popular. It's a fact that many academic institutions have centers of excellence in VLSI, in microelectronics. What is not well known by many people is magnetics as an area of technology, which is electrical engineering, is actually in volume much larger than electronics, or microelectronics. The microelectronics industry in this country is roughly 14 billion dollars. The magnetics industry is $20 billion. And yet, very few universities are conducting fundamental research in magnetics. A handful of institutions. My institution happens to be one of them. It's not the only one. The message here is that magnetics technology is a coming area. It's an important one, and it should receive, it's already receiving attention from industries. In fact, there are several centers of excellence now, well funded by industry and also funded by the Department of Defense. More to the research which is being conducted in universities almost from the beginning. Many of the advances in computer architectures started in universities, MIT, Stanford, Carnegie-Mellon, Berkeley. In fact, the very same universities which attracted funding from DARPA, the Defense Advanced Project Agency. Computer science and DARPA have had over the years a very close association. It's fair to say that without DARPA, there would not be computer science departments or sub-departments in this country. Much of the fundamental research, the creation, in fact, of the discipline can be ascribed to the funding from DARPA. Artificial intelligence, which is a component of computer science and therefore is a part of electrical engineering in some institutions, without funding from DARPA and some funding at the beginning from the Office of Naval Research, we would not have made that progress we have made in artificial intelligence. And I don't have to tell you that the beginnings of artificial intelligence were conducted in universities. Industry now are users, and I'm not saying that they are not contributing. They are contributing a lot, but always closely connected with universities. Expert systems is a branch of artificial intelligence, and I think it has been mentioned as a topical area, which is extremely interesting now for universities, but it's a tremendous use for industry and for the Department of Defense. Manufacturing and flexible automation. I talked before about adaptive control, which began in universities, particularly at MIT after Second World War. Flexible automation in manufacturing, including flexible automation and manufacturing in electronic circuits, is probably now the newest, hardest area of interest, because here is where this country is in a tremendous competition with Japan and with West Germany. Robotics, which is just a small component of flexible automation, has received a lot of attention, particularly from you people, because it's glamorous and it's sexy. The robot is nothing more than one of the components of a flexible automation system. Might not be the most important part. Supercomputers, I won't say much about supercomputers because it's going to be a topical area in one of the sessions. I am very proud to say that many of the advances which are going to give rise to the future supercomputers, and we already have supercomputers, are in universities, and they were funded by DARPA in universities. Software engineering. Leo Young say a few words about the Software Engineering Institute, which is an initiative which is going to be started very soon. I think there is already a line item on the budget. And of course, there are a few universities scrambling for where the Software Engineering Institute is going to be. We hope that will be in Pittsburgh, near Carnegie-Mellon, but we are not the only contenders, although we are powerful contenders. This is a nice word for Leo Young. He's going to be one of the decision makers. Software engineering is going to be probably the most important area of development for universities, for industry, and for the government to sponsor and to work together. Here we are not talking about computer science. As Leo Young mentioned before, we are talking about straight engineering, very applied, the maintenance of the programs, whether it's Ada or another languages. Software engineering is to do what it takes to make the supercomputers and the very spectacular programs to work reliably. Next transparency, I think I am done. In conclusion, the universities have played a role in advancing state-of-the-art in computers, in electrical engineering, in microelectronics. They are going to play a bigger role in the future. The role has to be playing closely together with industry and establishing the three-pronged connection. Funding from the government coming to universities, funding from industries coming to universities, very close coordination of the three. And this is...
Thank you very much. Again, we'd like to entertain some questions. Yes, sir.
Sam Greenberg from Defense Science and Electronics. You mentioned magnetics, and I believe a $20 billion annual research expenditure in the magnetics area versus 13 to 14
No,
billion.
I mentioned volume, the total volume of the magnetics industry, which are peripherals,
Okay, for the
recording is roughly $20 billion in this country.
Beyond its size, what are you referring to in terms of magnetics as a burgeoning research area?
Okay.
What are we talking about? Signal processing?
What's the payoff?
Yes.
Where's the payoff? The ability to record tremendous amounts of information, okay, closely packed. At the moment, you can do much better with magnetics than you can do with semiconductor memories. And I don't care how small your computers are going to be, the PCs and the chips, you still need disks, disk drives, you need secondary memory. People are playing tricks with virtual memories, but you still need floppies, hard copies, you need ways of storing information much more densely packed. This is magnetics, magnetic recording.
You focus then on the magnetic data storage. Does that put it in competition with optical data storage, or
It
do
is in
you group them together?
I group them together. You are correct that in the future, optical storage probably is the way of the future, but it's not here yet. And the two of them are not incompatible.
Any other questions? Yes, sir.
In connection with the changing relationship with defense in the universities, how about the problem of publication of results?
Pardon me?
How about the problem of publication of results?
Okay, this is a very good question, and I expected it. And I think there are a couple of professors in the back of the room too. The policy of universities, and sometimes it's not easy, but we try to accomplish it, is to have, we like to retain publication rights. And often, we give the patent rights through licenses, although they belong to the university, to the sponsors. But we insist, I said at the beginning of my presentation, that students, people, are our most important product. Harvey Nathanson, when he was my student, had to publish 2 or 3 papers. Otherwise, I wouldn't give him the diploma, okay? And I wouldn't get 2 or 3 papers for me to be promoted. This is not this is humorous remark, but the fact is that the university role is to create or help create and disseminate knowledge for the purposes of education. So in any agreements with the Department of Defense, we don't have a problem because we don't do classified research, okay? But with industry, occasionally we have to enter into agreements and we have to insist that we retain the publication rights. That does not exclude doing pragmatic work. Often the pragmatic work is done and we don't publish the specs of what we are doing, but we publish the generic scientific engineering content.
As the chairman, I guess I'm allowed to ask one question, and this is addressed to both Dr. Young and Provost Jordan. Work does not have to be classified, and still publication is a problem, particularly when it results in export to foreign countries under the Export Administration regulations. How does DoD, with its expanding role in the universities, going to cope with that, the dichotomy? It's a hard question. You might want to think a little bit about that. Leo, on how do you have any?
Why don't you answer the question, Leo, and I'll amplify.
I knew this would come up sooner or later. Let me try and answer it as briefly and simply as I can. First, the whole situation is very much in a state of flux. Harvey quite rightly pointed out the real problem area is the unclassified, sensitive information. If it's classified, everybody knows how to deal with it. It's normally not done on campus. If it's done by a university, it's usually done at a place like Lincoln Lab or the Johns Hopkins Applied Physics Lab. If it's unclassified, unlimited distribution, wide open, again, no problem. The focus, the spotlight, has been on that area which is unclassified, but limited distribution, export controlled, sensitive. Now, the DoD policy on that is we divide the world into two parts, basic research and the rest. When it comes to basic research, first, again, if it's not sensitive, unclassified, etc., no problem whatsoever. When the author wants to submit a paper to a journal, he just goes ahead and submits it. DoD does ask him to send us a courtesy copy. If there are comments in the courtesy copy, whatever they might be, obviously they could be fed back, but the responsibility is entirely with the author of the university. If, on the other hand, the work is unclassified but sensitive, it has been agreed, and is our policy, that that would be stated in the contract. In other words, we would not come in the middle of a contract and say to the university, oh, by the way, this is sensitive, and the rules are different. We would have to say so at the beginning, so both parties would understand, and the contract would be used to control it. In other words, it would be agreed on just what should be done. As far as publications are concerned, the following rules then apply. If it is agreed that the work is sensitive, then the way it's being dealt with is essentially much the same as an industry might require when it deals with a university. DoD asks for a delay in publication. What we then ask is that the work be submitted to DoD for review, not for approval, for review, and a 60-day delay applies. If the university hasn't heard of 60 days, no problem. If the university has heard within 60 days, we simply ask them to take into account whatever comments are received. They're only advisory. The decision to publish or not to publish, what to publish or what to leave out, is strictly with the university. The only effect is the 60-day delay, which gives us a chance to comment. There may be something sensitive, this may be agreed, and no editor or reviewer has seen it. Now, when it gets into the more applied area, the rules are a little more complicated.
Thank you, Leo. Yes, sir.
Jerry Green, Microwave Journal. Getting back to magnetics, could you give us some of the goals in the magnetic technology that you hope to achieve with this $20 billion being spent annually?
Well, basically, the goals is to take care of the fact that very few universities are conducting fundamental research in magnetics for the next generation of magnetics. The goals are, at the moment, there are 2 or 3 centers of excellence. One happens to be at Carnegie-Mellon, my institution. Another one is at the University of California in San Diego. And there are small efforts at Minnesota, MIT, and Stanford University. The goals is to mark and plant the next generation of magnetic recording, which is magnetics and is optics, both. And to plug in the void for the fundamental research. Much of the research much of the developments in magnetics is actually quite old. The new frontiers of magnetics, particularly in combination with electronics, conventional microelectronics, still have to be tapped. We have to prepare ourselves for the supercomputers and the super memories which will be needed with the supercomputers. It's not just only software development, it's new ways of storing information. The Japanese, again, are a bit ahead of us in the technology. In some of the fundamentals, as usual, we have the answers, but there is not enough research conducted in universities, and even the Department of Defense, which all my bragging about the Department of Defense funding research in universities, in this particular area, they are not doing enough. I'm sorry, Leo, but this is my message.
No, but could you be more specific? I'm looking for something tangible in the magnetic area.
The ability,
For example, you mentioned the micron, submicron area of VISIC.
okay.
What do you hope to achieve in magnetics?
You want to answer that question, or you want me to answer the question?
Well, let me just say this. I fully agree with Dr. Jordan. The research in magnetics is proportionately much too small. The applications, however, are largely commercial, much more so than they have been in the defense area, although this may be changing now. I once did an analysis several years ago looking at the proportion of R&D in magnetics that was done on DoD contracts as distinct from what I just call the IR&D, which is the money that DoD provides but is considered to be industry money. The proportion of research in IR&D in magnetics was much higher, like 10 times as much proportionately, as directly in contracts. In other words, there was tremendous commercial interest. This is distinguished from, let's say, microwave tubes or lasers, where it was just the other way around, where the contract work DoD sponsored was much higher, the commercial interest was much less. It's heavily in the commercial area, is what I'm saying.
I think we have time for one more question.
I think we left him a little puzzled. He's looking for something more tangible. He wants a number. The ability to store billions of bits of information, which some of our secondary memories with semiconductors do not have. Indeed, with the micro and submicron technology for logic and for memories, the storage capacity is extremely large. With magnetics, will be even larger. You can dense. It lacks the ability to do logic because the magnetic is slower than microelectronics. But the density of information you can pack and you will be able to pack is considerably higher.
Thank you. Oh, yes, sir.
Why, with the advent of optical memories, why do you need so much emphasis on magnetics? My understanding is that you can store so much more information, so much more densely with optical memories, and you say they're incompatible, but why can't you make them compatible?
Excuse me, I said that they are compatible.
Oh, they are compatible.
They are
I'm sorry.
compatible. There are issues of reliability and cost. Optical memories, although indeed they have more capabilities than magnetic memories, are still not cost effective. The technology, the rudimentary technology in magnetics, with the new advances which are coming from science and technology and signal processing, lend themselves to a quicker progress. Okay? Indeed, the two technologies will be coupled in the future. And they are already beginning to be coupled.
Okay, thank you very much, Provost Jordan. As our last speaker, it's my pleasure to present H. Warren Cooper. Mr. Cooper is currently manager of the Solid State Systems Group at the Advanced Development Division of Westinghouse Defense in Baltimore, Maryland. Mr. Cooper received his bachelor's degree in 1947 from New Mexico State University and his MS from Stanford University in 1948. Warren's IEEE activities include president of the Microwave Theory and Techniques Society of IEEE, and he was again elected fellow in 1970 for contributions to antenna development and microwave techniques. I'm very pleased to present Mr. Cooper, who, by the way, has a very key appreciation of the role of technology in advanced avionics systems, a key man in our Westinghouse team, who will speak on the new commercial defense synergism. Warren?
Thank you, Harvey. I'll address the new commercial defense synergism. I think we have a current defense commercial synergism, but I think we want to look at the factors that are involved in this synergism and where we are going to go to address the supercomputers and so forth that have been mentioned here this morning, and it will be mentioned further by Bob Cooper and others this afternoon. I think if we may have the second view graph, Harvey. I think that there are some points that I want to make on the synergism. I mean, the whole purpose of it, the whole is greater than the sum of its parts. As Leo and Dr. Jordan mentioned this morning, people make it happen. And another point that was made, our last one here, people make it happen through technology. And then I think a very key point, sort of related to this meeting here this morning, the IEEE is an organization that provides a framework for making it happen. Now, I think that that is a key point that we have to recognize in the IEEE, that this synergism that we have between industry and government, I think comes in large part through the volunteer organizations such as the IEEE. Moving on to the next chart, there are various technologies in the area of new defense and commercial synergism, and I'm choosing to address the semiconductor technology, talk a little bit about the silicon technology. Next chart, please. And also, I want to mention that in talking synergism, it interacts with the Leo's talk and Dr. Jordan's talk this morning, and the health area, Dr. Budinger and Dr. Mann this afternoon, and the supercomputers, Bob Cooper, 3 o'clock or 3:30 this afternoon, and the power and telecommunications area. So that, in other words, this interacts with all of these areas of technology. Next view graph, please. Now, the reason I chose the semiconductor area is because this impacts the IEEE really greatest, I think, as it has impacted the civil economy in the area of computers, games, digital watches, etc. And I think that the semiconductor area has been strongly built on silicon, and silicon will continue to be a strong foundation for it, but we're moving into a new material for military applications and for some civil applications, such as low noise receivers for direct broadcast satellites and so forth, and that's gallium arsenide. Now, I think that the gallium arsenide is a material that offers a lot more speed and higher frequency coverage than you can achieve with silicon, and as a technology it interacts with a number of the societies in the IEEE. Next view graph, please, Harvey. I think that the key societies that are involved in the gallium arsenide technology are the Microwave Theory and Techniques Society, the Electron Devices Society, and the Circuits and Systems Society. Now, I think that this is a very key technology, and the IEEE societies provide a forum for the interchange of information in this area, in this new area, as well as in the other areas that you see in this list of IEEE societies here. But the key thing is that the synergism that we get between industry and government comes as a result of the people, as well as a result of the hardware, the manufacturing facilities and test equipment that are made available for both the civil and commercial and for military activities. And the next chart, I've tried to diagram what the history has been in the synergism in the silicon industry. Really, I think that we got into integrated circuits through some strong DoD support in the early, late 50s, early 60s. As I understand it, there was a Marine Corps colonel that really did a tremendous job in selling the Navy on going with integrated circuits for their reliability, small physical size, and so forth. And that was enough to get the thing started. Then the application of this to computers in the digital area and in the linear area to ultimately radios, TVs, and all of the various personal consumer items that we have, as well as things such as air traffic controls systems. And as a result, this one technology has, I think most of the magazines seem to agree that this has probably had more impact on our society than any other advance that has been made in recent years. In any event, this synergism in silicon between the military and the commercial has put in place a pretty extensive manufacturing base. Now, this manufacturing base provides the technology for handling semiconductor wafers, for a high-resolution lithography, for creating the integrated circuit patterns on these wafers. And it's this production base that has allowed us to go forward to the VLSI and to the VISIC programs, such as Leo and Dr. Jordan mentioned this morning. Also, it has permitted us to go to power silicon devices that are operating in the UHF and low microwave frequency region that are used in the air traffic control beacons, which are going to be the basis for the collision avoidance systems of the future. Also, the use of this beacon is going to permit us to use just the secondary radar instead of the primary skin return radar in the traffic control systems, and I believe in Europe it's already done that way. Now, moving on to the next view graph, I have tried to identify here the difference between silicon and gallium arsenide. In other words, we have gone from the first silicon transistors costing several $100s to a place where you can get a digital watch for $3.50 that keeps time to an accuracy of maybe a second a month or so. Now, that has come about, and I don't know whether you can read this, but in essence, I think the key thing is we went from a silicon boule originally 15 millimeters in diameter to now we have one that's 100 millimeters and I think even more now. And we went from 80 micron design rules on the lithography down to 4 microns commercially. VISIC is down to 1.25 microns, and we're talking half micron for future applications. Now, all of this gets more circuits per wafer, and in general, the processing cost is on a per wafer basis. It doesn't matter what the size of the wafer is, whether it's an inch in diameter or 5 inches in diameter. The processing cost is the same, so pretty much the reduction in cost of the circuit results from the increase in the number of circuits per wafer. And you can get that by increasing the diameter of the boule and the slice on which you make the semiconductor, and by reducing the feature size. However, if you get over into gallium arsenide, I think that the key thing there is that we are talking really about analog circuits rather than digital circuits. In other words, we use them for microwave amplifiers, and while the same high-frequency characteristics that make it good for amplifiers are also good for high-speed logic, still, in order to get the advantage of these amplifiers, we have to use reactive circuit elements to provide the interstage coupling and so forth, so that it turns out that the limitation on the number of circuits in gallium arsenide that you can get on a circuit, on a wafer, is determined by the size of these passive elements as opposed to the size of the resolution of the features that you can get using high-resolution lithography. In other words, the bottom line is, in the silicon industry, from the time that we had our first silicon transistor, our first integrated circuit, to now, we have had a yield and circuits per slice improvement of something in the neighborhood of 2 to 4 times 10 to the 5th. However, in gallium arsenide, it looks like, based on what we know of the technology today, we are going to get an improvement between 1 and 500 times what we are able to do today. And that's because the circuit size is determined primarily by the area needed for the high interstage, by the interstage passive reactive elements. Moving on to the next view graph, what this means is that in terms of silicon circuitry, the experience has been pretty much a learning curve of something of the order of 70%. In other words, the learning curve percentage is the amount by which the average cost reduces in doubling the quantity of circuits. And I think that the other thing is, too, the sheer quantity of circuits that have been produced in silicon. In other words, the cumulative quantity produced is something in the neighborhood of 1 billion or more, and so that this has allowed us to move down the learning curve. In the gallium arsenide arena, this is not the case. We are going to have a lot fewer circuits, and the learning curve at best is probably going to be something in the neighborhood of 80% as opposed to the 70% for silicon. Moving on to the next slide, what I'm calling the new synergism in gallium arsenide technology is one that's based on the military commercial synergism assisted by the IEEE interactions, meetings and conferences. The Microwave Society, the Electron Devices Society, and others have meetings and conferences in the area of gallium arsenide materials, devices, and systems. You get your circuit development, then you move on down. We currently have low noise receivers that are made monolithically. These are addressing the direct broadcast satellite market. I mean, which market may or may not come. I think it's interesting, if you noticed in the Post back in January, I think U.S. Communications or something has started selling direct broadcast satellite service. However, I think in the latest Fortune, the director of, or the chairman of the board of Tandy said that they weren't going to get into it until they have their financing in place because they aren't sure that it's really going to go. So in any event, I think it is going to go. I think that this is an area where monolithic gallium arsenide will find a market, both in the monolithic low noise receivers and in the power circuitry that's used for providing a high reliability transmitter in the satellite itself. The high frequency, high speed characteristics of the gallium arsenide circuits will be applicable for digital computer, for the digital circuitry for supercomputers. Again, in designing this sort of thing with the high speeds that we're talking about, microwave techniques have got to be used for its design in order that you don't lose it all in the interconnections. Optical fiber communication is another area that is really key, because and there you have the gallium arsenide and optical that is microwave and optical interaction. You have opto-FETs, where you use the photons to modulate the microwave energy, and that then will have a direct impact in communications and cable TV. I mean, the telephone companies have already got many miles of optical fiber in place, not modulated at microwave frequencies, but they will be getting close to it in the coming 5 years. And then all of this technology in gallium arsenide is going to result in the ultra-high data rate systems of the 21st century. In other words, you'll start seeing this stuff getting into place in the mid to late 1990s probably, and then it will be fully fielded and fully applied in both the military and commercial environment in the 21st century. But it takes a long time to get there. I mean, you just look back on silicon, when we started with silicon and how long it's taken us to get to the $3.50 watch or clock. Now, I think a good indication on the next view graph of the activity in gallium arsenide is the number of papers that are published. Now, I think this sort of shows the relationship. Optical includes microwave modulation of optical signals, which will have application again for the optical communication. And you'll notice that in gallium arsenide, the optical area is the largest. The digital area is the smallest. Now, again, you have an overlap. There are 3 papers that are optical and digital, and there's one paper that's, this is in the past, in 1983 and 84. There's one paper that includes all 3 subjects, but again, this is a good measure of the activity in the field. Now, one thing that might be of concern is that half of the papers represented here are non-U.S. papers. I mean, the Japanese, the Italians, the French, and so on are in there very heavily. But again, I think that this is a good measure of what you see in this technological field, which is going to be a field for the future because of our requirements for a higher data rate and so on. Moving on to the next view graph, this is just sort of a summary. I think that the application of gallium arsenide power devices is primarily in things that radiate, like radars. In other words, most of the civil and consumer products, except for those in communication systems, in aircraft radars and so forth, are receiving systems, and they do not have the large demands on square inches of gallium arsenide that the power devices do. Moving on to the next slide.